In this video, we talk about computing limits analytically. We're going to discuss limits of known functions, including primarily continuous functions. We'll talk about limit laws. We'll talk about the limit of a composite function. And then we'll talk about 3 methods for eliminating 3 different types of 0 over 0 indeterminate forms by factoring and reducing, multiplying by the conjugate, and clearing complex fractions. So let's say you have a function y equals f of x. We say that f is continuous at x equals c. If the limit as x approaches c of f of x equals f of c. So that means when you compute the limit as x approaches c from the left and the right, the y values just approach the function value there. So the limit exists, the limit from the left and the limit from the right are the same, and it's equal to the function value. Now we say that f is continuous on an interval. From a to b, if f is continuous at every point on that interval. Or at every x value in the interval from a to b. So this function is continuous on the entire real line, provided that these arrows continue in both directions. Intuitively, we say that f is continuous on an interval from a to b if we can draw the graph of f without picking up our pen. So I can start at the beginning and then just keep going to the end. And I don't ever have to pick up my pencil or pen. If that's the case, then we say that f is continuous on that interval. So that's the idea. Now this is going to allow us to compute the limits of lots of known functions. Most of the functions that we've studied in pre-calculus are continuous functions. So polynomials are continuous. Rational functions are continuous on their domains. Radical functions or root functions are continuous on their domains. Of course, our trig functions are continuous. Inverse trig functions are continuous. Exponential functions are continuous. And logarithmic functions are continuous on their domains. Pretty much everything that you've studied, with the exception of maybe the greatest integer function, is continuous on its domain. So for example, if I draw a polynomial, let's say we have y equals x minus 2 squared times x minus 1, or let's say x plus 1. So if we distribute that, it's x minus 2 times x minus 2 times x plus 1. We multiply these two together, we get x squared minus 4x plus 4. If we distribute the x to all of this, we get x cubed minus 4x squared plus 4x. If we distribute the 1 to all of that, we'll have a plus x squared minus 4x plus 4. And so we'll get x cubed minus 3x squared plus 4. That function kind of looks like this. When x is equal to 2, we get 0. When x is equal to negative 1, we get 0 as well. When x is equal to 0, we've got 4 times 1, which is 4. And as x goes to infinity, this x cubed term dominates, so the function's going to go to infinity. As x goes to negative infinity, this x cubed term dominates, so the function's going to go to negative infinity. So it's going to rise on the right and then fall on the left. And then because of the multiplicity of these roots, since this is squared, since it's an even, since this factor is raised to the second power and that power is even, our graph is going to touch and turn at the x-axis. And because this multiplicity is odd, it turns out that the graph crosses through the x-axis. So roughly, our graph is going to look like this. Now this function is continuous at any x value on the interval. So at x equals 1, of course, this is not to scale. You might be interested in what the y values are approaching. If we had drawn our graph to scale, we could just read the graph. We could say it's x equals 1. What are the y values approaching? But since I don't actually have a graph that's drawn to scale, I can evaluate this limit sort of algebraically or analytically. The limit as x approaches 1 of x cubed minus 3x squared plus 4 is simply the answer that you would expect. If you plug in x equals 1, you get 1 cubed minus 3 times 1 squared plus 4. So 1 minus 3 plus 4, or 5 minus 3, which is 2. So the limiting value is 2. I guess in this case, it's closer to scale than I thought. At least in the neighborhood of 1. And so as x approaches 1, we get 2. Well, you might say, well, what does the graph look like as x approaches 100? Well, I don't know. It's kind of a pain to draw this graph all the way out to x equals 100. But I don't really need to because it's a polynomial. And I know that polynomials are going to be nice and smooth and continuous on the entire real line. So the answer is just going to be x cubed or 100 cubed minus 3 times 100 squared plus 4, whatever that answer is. And of course we would simplify that if we were solving a problem like this on a quiz or a test. But the idea is this function is nice and continuous. I would draw the whole graph of the function without picking up my pencil. So all I have to do to evaluate this limit is plug in c and simplify. And that's true for polynomials. Rational functions are similar. Now, I'm not going to come up with the equation of this particular rational function, but if my rational function looked like this, let's say I've got a vertical asymptote at x equals 2. Well, I know that for this particular rational function, x equals 2 is not in the domain, but the x values can be any other real number. In that case, if I was taking the limit as x approaches a of that rational function, well, the y values are going to be exactly what I would expect for the rational function. So in general, if I have the limit as x approaches some constant of f of x divided by g of x, where f and g are polynomials, and that's again the definition of a rational function. It's just a quotient of polynomials. then the answer will be f of a divided by g of a. You just plug in x equals a, provided that g of a is not equal to 0. Because if g of a were equal to 0, we'd have a vertical asymptote there. So we'll just say as long as g of a is not equal to 0. But this is continuous. I can draw this piece and then this piece without picking up my pencil. I do have to pick up my pencil to go from one branch of the rational function to the other. But the idea is the same. The function is called continuous on its domain if we can plug in that value for any value in the domain of the function and get the right answer for the limit. And that's what will happen for any rational function. Now, even if I don't know the equation, or excuse me, even if I don't know what the graph looks like, let's say I'm taking the limit as x approaches 2 of x plus 6 times x minus 3 all divided by x plus 5 squared. Say, well, that's a rational function. Is it continuous at x equals 2? Well, yeah, this is well-defined at x equals 2, and the denominator is well-defined at x equals 2. So what's the value of the limit? Well, it's just going to be 2 plus 6, which is 8, times 2 minus 3, which is -1, all divided by 2 plus 5, which is 7 squared. So you end up with a -8 over 49. That's going to be the y value on the graph. At x equals 2, the y value on this for this particular function is this. Now, this particular function, because the denominator is 0 and x equals -5, has a vertical asymptote x equals -5. But otherwise, it's going to be continuous everywhere. And if we wanted to, if we knew more about, well, we're going to study later how to think about other features of the graph so that we can graph it in general. But again, rational functions are functions that are continuous on their domains. Basically, if you can plug in the number and you get a number out that makes sense, you're not dividing by 0, then it's totally fine. Just go ahead and plug in the number. The same thing is true for square root functions, cube root functions, fourth root functions, any expression with a rational exponent. So if we have the limit as x approaches a of x to the n divided by m, the answer is going to be x to the n divided by m, evaluated at x equals a, excuse me. So we'll have a raised to the n over m power, provided that actually makes sense. So for example, if I have the limit as x approaches 32 of, let's say, x to the, let's say 3/5 power. And then we're going to get 32 raised to the 3/5. And if you remember from your pre-calculus or your high school algebra classes, raising a number to the 3/5 power is same as taking the 5th root of that number and then cubing it. The 5th root of 32 is 2, because 32 is actually 2 to the 5th. 2 times 2 is 4, times 2 is 8, times 2 again is 16, and then times 2 again is 32. So you've got 2 to the 5th, and you're taking the 5th root of that, so you just get a 2, then you cube it. So you've got 2 cubed, which is 8. That function is going to be continuous, and every x value where it's defined, and it turns out that it's defined for all real numbers, because you can take the 5th root of any real number. If this number in the denominator is even, you have to be careful. You can only take well, you'd be taking an even root. And if it's an even root, this number inside has to be non-negative. But provided that you get out a number that makes sense, that you can plug in that number and get an answer out that makes sense, it's not a complex number, then this function is continuous. All you have to do is plug it in. And that's just an example of a radical function. Even though it didn't have a radical in it initially, just had that rational exponent, the radical was implied because that 5 in the denominator implies a 5th root. So we've got radical functions, trig functions are continuous on their domains. just because of the intuitive definition. Our sine function looks like this and it just repeats forever, right? That's obviously continuous on its domain. Our cosine function looks like this and it repeats forever. So that's continuous on its domain. You might say, what about tangent? Tangent's not continuous. Well, it is continuous on its domain. You do have to pick up your pencil a whole bunch of times, infinitely many times actually, to draw all of the branches. But on each branch, it's continuous. And we have issues here. This is y equals tangent of x. Our tangent is sine of x over cosine of x. We're going to have problems whenever the denominator is 0, and the denominator is 0 at all the odd multiples of pi over 2. Set x equals negative pi over 2, we're going to have an asymptote. At x equals positive pi over 2, we're going to have an asymptote. 3 pi over 2, we're going to have an asymptote. 5 pi over 2, we have an asymptote. So pretty much every time we take the cosine of an odd multiple of pi over 2, we get a 0 in the denominator. But as long as we're not at an x value that's an odd multiple of pi over 2, that function is continuous. So if someone asks you, well, what's the limit as x approaches, let's say 5 pi divided by 4 of tangent of x, you say, well, it's just the sine of 5 pi over 4 divided by the cosine of 5 pi over 4. And if you don't remember that, you can always draw a triangle. 5 pi over 4 is going to give us a triangle that's over here. The sine of that angle is, well, actually, if it's a 45-degree angle here, pi over 4 is our angle here, we're going to have a 1 square root of 2 triangle. Since we're in quadrant 3, the x is negative and the y is negative, so we'll have negative 1 for our adjacent side, or negative 1 for our opposite side, and then a square root of 2 for the hypotenuse. So the tangent is just that negative 1 divided by negative 1, so we're going to get a positive 1. Or you can take negative square root of 2 over 2 divided by negative square root of 2 over 2, and you'll get 1 as well. But you just say, can I plug that number in and get out a number that makes sense? Yes, you can. So just go ahead and plug in the x value, and we get 1. Now, if I was asked for the same, or for the limit as x approaches pi over 2 of tangent of x, I'm going to have a problem, because as I approach pi over 2 from the left, my function goes to positive infinity. As I approach pi over 2 from the right, the function goes to negative infinity. So we get two different limits, and not only are they different limits, they're infinite limits. So technically those limits do not exist, even though they don't exist in very particular ways. So that's a bit of a problem. But on its domain, the tangent function is continuous. Pretty much all of our trig functions are continuous on their domains. You just have to worry about those points, those x values that cause the denominator to be 0 when you're talking about tangent of x, cotangent of x, cosecant of x, and secant of x. And I think that covers it, all those that would have sine and cosine in the denominator. Okay, so polynomials are continuous on their domains, rational functions are continuous, radical functions, trig functions, inverse trig functions. The exponential functions all have the same basic shape. Exponential functions look like this. In general, y equals a to the x, where a is a constant. A is a constant that is not equal to 1. And if it's greater than 1, it's going to look like that. If a is less than 1, it just goes the other way instead. But that's what an exponential function looks like. It's obviously continuous. You can just draw it from negative infinity to infinity without picking up your pen. That's a continuous function. Somebody asks you, well, what is the limit as x approaches 3 of 2 to the x? Well, it's just 2 to the 3rd. It's just 8. It's exactly what you would expect. And it's, if you want to graph it, not to scale. It's going to look like this, basically. as x approaches 3 from the right. Our y values approach 8 as x approaches 3 from the left. Our y values approach 8, and that's the same as the function value there. And logarithmic functions have a very similar shape, but we sort of flipped them twice. So that's y equals natural log of x, for example. That's continuous on its domain, and its domain is 0 to infinity. So if you can plug in an x value there and get out an answer that makes sense, then it works. You can't take the log, that limit's going to be the right thing. So if I said, what's the limit as x approaches 5 of natural log of x, it's just natural log of 5. That's no problem. But if we took the limit as x approaches 0 of natural log of x, we are going to have a problem, because as we approach 0, the y values go to negative infinity as we approach 0 from the right, and the y values don't even exist as we approach 0 from the left because there's no graph over there. So we need to remember the domain of the logarithmic function. We need to keep in mind the domain of a rational function. We can't divide by 0. We have to keep in mind the domains of trig functions. Again, you can't divide by 0. So anytime you've got a cosine or a sine in the denominator, you're gonna have a problem. And then we have some domain and range issues with the inverse trig functions as well. But as long as you know those functions and you know where they were defined, evaluating the limit is very simple. You just plug in the value and it gives you the right answer. You might have problems if you don't remember what those functions are and what they look like. So if you don't remember that tangent of x is sine of x over cosine of x, or you do remember that, but you don't remember when cosine equals 0, then we may have to review that in order to compute the limits of these continuous functions. Okay, so I guess that was a lot. I think we'll stop there. We'll talk about limit laws next time and limits of composite functions, and then maybe in a third video, we'll do the indeterminate forms. This one took a little bit longer than I thought. So I hope that's the idea. Let me know if you have any questions. Thanks.